Next. Okay. Can you all hear me? Awesome. Great. So good morning, everyone. My name is Clémence Fontanive. I'm a postdoc fellow at the University of Montreal. I'm going to go lower down in mass and tell you about the James Webb Binary Survey looking at the very lowest mass brown dwarfs. So this is very much a collaborative effort. I'm presenting this on the behalf of an entire team of amazing people listed here. Many of them are here this week, so please go talk to them about the awesome work that they've been doing for this. So in the context of this temperature sequence, where we have low mass stars, then going down through brown dwarfs all the way down to Jupiter, I'm going to be exclusively talking about these objects down here called white dwarfs. So these have effective temperatures. Yeah, I'll do my best to enunciate, but there might be some ambiguities. I'll also occasionally say the words wise and wide, but hopefully they'll be clear from context. So they have effective temperatures below 500 Kelvin, masses up to 25 times that of Jupiter. So they really are representing the very bottom end of star formation, which makes them a really valuable population to study in terms of demographics in our solar neighborhood. Okay. So in terms of multiplicity, we've heard a few times this week about this known trend of decreasing binary fraction with later spectral type. As a brown dwarf person, I want to highlight that this trend actually is not just for stars, it extends across the boundary between stars and brown dwarfs. And it even appears to persist throughout the brown dwarf regime, all the way down to the very latest type T dwarfs that have a binary fraction of 5 to 10% only. But as we're now entering the white dwarf regime, we don't actually know much about the multiplicity of white dwarfs. Very few of them have been targeted for binarity. The few that have been resulted in null detections. But these observations were really limited in sensitivity because these white dwarfs are so cold and so faint and so challenging to observe. So we probably expect white dwarf binaries to be quite rare, but we haven't formally confirmed this yet. So that'd be a good thing to do. And who knows, maybe something unexpected will await us. Then the second thing I want to highlight is that brown dwarf binaries tend to have tighter orbital separations than stellar binaries in the field. So we see a binary this separation distribution peaking at only a few AU for L and T dwarf binaries. But if I plot these same binary systems in terms of their angular separation in the sky, there's suddenly a really sharp drop-off in that distribution, which actually coincides roughly with the resolution of the telescopes that we have been using for these surveys. So that tells us that we're probably missing more binaries at the tightest separations, and that this peak that we're seeing may not be the true peak of the distribution, and it could be closer in. So this means that we may not have the full picture yet with that story that I showed you on the left. And it definitely suggests that if we want to study the very latest type binaries, we really need to probe the very tightest orbital separations. So based on this, we were awarded time on James Webb during cycle 1 to observe 20 of the currently known white dwarfs with NIRCam to search for close companions around these. So this is a program led by Loïc Albert, who is here this week, and Michael Mayer. And we have 3 main science goals with this program. The first one is to exploit the unprecedented infrared sensitivity of James Webb to cold objects like white dwarfs and its unprecedented spatial resolution at these wavelengths. To probe for the first time the multiplicity of these white dwarfs and explore the very bottom end of star formation through binarity. The second is to try to find some of the very coldest objects out there by searching for them around the already very coldest objects out there, so that we can hopefully better populate the really sparse sample at the very cold end of this sequence and maybe even further extend it to colder temperatures, finally bridging what we know to Jupiter. And finally, because I'm focusing here on fairly tight orbital separations, it means that any system we might discover would be amenable to orbital monitoring, which means that we could get dynamical masses over just a few years. And that would be really valuable to constrain theoretical models in this new, very cold temperature regime where we don't have much empirical validation for models yet. So observing strategy is pretty straightforward. We observe all these 20 white dwarfs in 2 different filters with NIRCam. So the one on the left, the little white dwarf here is in the yellow circle. The filter on the left is in the near-infrared. The one on the right is in the mid-infrared. Because these objects are so cold, most of the flux comes out in the mid-infrared. So you can see that it's a lot brighter in the right image. And any companion that we might find around these objects would be expected to have similarly red, if not even redder colors. So we can use this dual band photometry to validate the nature of potential candidates based on their colors. So then we search for companions at close separations with two different approaches. The first one is through PSF fitting. So I'm going to show you an example of that in a bit. The second one is kernel phase interferometry. Talking about interferometry in front of this many people is very high up in my list of nightmares. So please ask your questions to Thomas Vandel, who has been leading this analysis. And I will not say more about this. And then we also have a complementary work package to search for wider companions in the rest of the images, which is led by Daniela Badaret-Galgoufi. But today I'm going to focus about our results at the close angular separations. So we search for companions with these two parallel methods. Luckily, they do agree pretty well. We converge to the same results with both. And they both found one new binary. So this is the system, the object in the image that I showed you before. This is what its PSF looks like in the radar filter in the mid-infrared. So you probably don't believe me that it's a binary by just looking at this, which is fair. So what I'm going to do is to subtract a single PSF model from this. And what you see is that we end up with some pretty significant localized residuals up there at the top. So that means that the single PSF model was not doing a good job at accounting for all the light that we were seeing in this PSF. So the next thing I can do is to fit a double PSF model. And this time, it does a much better job at getting rid of these residuals, which tells us that it was a binary. And if somehow you still don't believe me, what I can do is to subtract only the primary from this binary PSF model in the middle panel so that the companion really pops out nicely behind the PSF of the primary. So this system is called WISE 0336AB. The components are separated by just under 1 astronomical unit, so it is fairly tight. We did find that the companion was fainter, but also redder than the primary, which is what we would expect for a low mass companion like this. It was really exciting for us because this is the very first binary system that we found that is orbiting around a Y-type primary. So the primary has a Y spectral type. It's the first time that we found a system that is this cold. We had cool stars. This is literally the coolest binary system that we've found so far. So we estimate a temperature just over 400 Kelvin for the primary. Its mass could be anywhere between 8 and 20 Jupiter masses, depending on the age of the system, which we have no clue about. And then for the secondary, it's most likely planetary mass. It's most likely below 13 Jupiter masses. And we estimate a temperature just over 300 Kelvin. And that actually makes it the coldest companion that has ever been directly detected so far. And it's most likely the second or third coldest white dwarf in the currently known sample. So that makes it a really, really valuable new benchmark in our current sample of white dwarfs, and a very important system for us. And it was very exciting, but unfortunately, it was also the only detection that we made. So now the next step is to go from one detected binary out of 20 observed objects to actual binary statistics, which is where I come in. So the first step for that is to establish the completeness of our survey. So decide what we could have detected and what we may have missed. So this map here is showing the system mass ratios that we reach as a function of separation in astronomical units. So we are complete down to mass ratios between 0.1 and 0.2 beyond 1 AU around all systems, and even at sub-AU separations for quite a few of our targets. These mass ratios correspond to mass limits around 1 to 3 Jupiter masses and possibly even down to sub-Jupiter masses if our systems are on the young end. And then for our best targets, we can even resolve a companion down to mass ratios of about 0.5 down to 0.3 astronomical units. And I'm now going to switch off the color map in this, but just keep these contours so that I can compare the sensitivity to an HST program that I recently led that was looking at late T on some of these white dwarfs for binary companions as well. And you can see that with this web program, we're reaching significantly deeper masses and mass ratios, and we're going much closer in terms of separations. So we're really probing a completely new region of the parameter space with web that was completely inaccessible before for these sort of objects. And then the companion that we found, which is in yellow over here, is not part of this HST program, but it does have similar HST data that we looked at and in which we couldn't recover the companion, which is not surprising when you see its location in this plot. So we really needed Webb to be able to make this discovery. Okay, so now that I have all this, I can finally run my statistical analysis. So for this, I want to take into account the completeness around all 20 targets so that I can account for what we could have seen, but also what we may have missed. I know that I have my one binary, and I take into account where in this parameter space it falls. And then I do have to make some assumptions on the ages of the systems, the evolutionary models that we use, the shapes of the underlying binary distributions. The good news is that we essentially limited statistically by the fact that it's 1 out of 20. So we are very robust to all these assumptions because this is not what's limiting us. So silver lining of small number statistics. So I put all this into my statistical black box, which I'm not going to bore you with, and it gives me a companion fraction around 6 or 7%. This is constrained for companions in this yellow box on the right here. So for semi-major axes from 0.3 to 10 astronomical units and mass ratios above 0.1. So there's nothing too surprising here. It is pretty consistent with what we expected in terms of binary fraction, but it is the very first time that we are constraining the multiplicity of these white dwarfs. And it's the first time that we are probing this new part of the parameter space. And the position, the separation of the one discovery that we did make is very consistent with this idea that the very latest type brown dwarfs, binaries tend to lie on tight separations. And just if I can have 15 more seconds. The next step that we'd like to do with this project, so our first priority is going to be to try to follow up this new binary and trace out its orbit so that we can get dynamical, so model independent masses for the first time for objects this cold. And then it would be nice to try to probe the rest of the white dwarf population for multiplicity, not so much to improve the statistics. We're not going to do that much better for now, but mostly because it does seem to be a really good way to find the very coldest objects out there. And hopefully that might be the best way to try to finally bridge that remaining temperature gap between known extrasolar objects and Jupiter. Thank you very much.
More Botsford from Berkeley. Thanks for a nice start. So we heard the other day about these jumbos. Those are, that's in a very young.
Yes.
I mean, they're very young. So later on, I suppose they would be the objects you were looking for. And to compare the binary frequency would mean to look at the free floating or Jupiter mass objects in Orion compared to the number of jumbos. Have we thought about that at all yet?
I have definitely thought about this, yes. So the question is about the jumbo discoveries that would be young analogs to these objects. So at the moment, what I presented is only at tight orbital separations, and because the jumbos are they're much more distant, it's a distant cluster. So we don't actually see things at like 1 AU separation, they're all really wide separations. But we are also constraining the wide orbit binary fraction, and we're not finding any equivalence to these. So what I think might be happening is that they're really low mass, they're really widely separated. The gravitational bound between the two components is really weak. So they're likely to get disrupted at some point during their evolution. And by the time we observe them as filled white dwarfs, we see them as single objects.